Hey folks, welcome back to our geometry class. We're starting a new unit today on right triangles and trigonometry. Whee! And we're going to start that with a lovely theorem called the Pythagorean Theorem. If you haven't watched my previous video on the proof of that, it's pretty helpful because we get into a lot of good stuff. So we're going to revisit good old Pythagorean Theorem and learn some stuff. All right, so inside the Pythagorean Theorem, I'm going to cut this video up. We're going to learn about finding a hypotenuse. We're going to learn about finding a leg, finding a distance, and classifying triangles as well with some neat applications of how the Pythagorean Theorem works. So let's jump into notes real quick. It's stuff you've seen in the past. I mentioned this in the last video, but I do want to explain it. If you've got a right triangle, if you have a right triangle, then you know that the sum of the squares of the legs is equal to the square of the hypotenuse. Okay? The sum of the squares of the legs is equal to the square of the hypotenuse. Now, what you have normally known as a squared plus b squared equals c squared, I would much rather you have knowing this. I'd much rather have you know this. That what it means. When we square the legs and add them together, we get the square of the hypotenuse. Okay, so in any right triangle, you have the square of the legs and add them together, you get the square of the hypotenuse. So, if a right triangle, then this is true. Okay? Now that is the Pythagorean Theorem. There is a converse of the Pythagorean Theorem that states if you have some triangle and it turns out that the sum of the squares of the lengths of two sides is equal to the square of the third side, then we have a right triangle. We will use this in classifying triangles in the next video. Okay, so if the sum of the squares of the two sides is equal to the square of the third side, we got a right triangle on our hands. Okay, but back to the Pythagorean Theorem. Now we have the situation where the sum of the squares of the legs is equal to the square of the hypotenuse. If that's the case, right, and that always is the case, if what happens if A, B, and C, if we find out that the lengths of the legs and the length of the hypotenuse, and it all fits into a right triangle, if they are all whole numbers, okay, if all those numbers are whole numbers, we have something called a Pythagorean triple. Okay, so if that's the case and it works out where everything is a whole number, okay, the legs are whole numbers and the hypotenuse is a whole number, we have something called the Pythagorean triple, and so we're going to work with that as well. Okay, so if this was confusing, pause, rewind, copy, but let's jump into some practice. Yeah! So, we're going to practice some things. So here we have a situation with a right triangle in our hands. We have two legs, 20 and 21. The goal is, what is the hypotenuse? And then wonder, do we have a Pythagorean triple? So, let's bust this out. Now we know from the Pythagorean Theorem that the sum of the squares of the legs, the sum of the squares of the legs is equal to the square of the hypotenuse. Now, the hypotenuse, I don't want to say is always C, but in your general notes, when you're working with stuff, it's normally your legs are A and B. The hypotenuse is C. Does it have to be C? No, you can call it J, call it K, call it Fred. Who cares? Just know that it's the hypotenuse. Call it X. It doesn't matter. As long as you know it's the hypotenuse. Anyway, not the point. So all I got to do now is some crazy math, right? So we're going to do some 21 squareds, which turns out to be, I'm using a calculator by the way, is 441. Okay, so we have 441. And then we have 20 squared, which is 400, and that's going to be equal to c squared. Okay? Now the only question is, well, what is 441 plus 400? Hopefully you know that's going to be 841. That's going to be equal to c squared. Now, if you recall, how in the world do we find out what c is if that's the case? Well, we have our 841, and what we're going to do is take the square root. Remember, square root undoes to the second power. Okay? Square root undoes to the second power. So they're all inverse operations. So we have the c squared. We're going to take the square root. That will show us what c actually is. And if we take the square root, we have to take the square root of both sides. So the square root of 841 turns out to be a quite friendly number, 29. Whoa, that is so convenient. So now we know that the hypotenuse is 29. And again, it doesn't matter that we call it C. We could have called it A, we could have called it B, we could have called it X, could have called it Fred. It doesn't matter. All we know is it's the hypotenuse, and it's 29 units, and that's important. So we now have found the hypotenuse. It's 29. The question is, do the side lengths of ABC form a Pythagorean triple? Now remember what we had established already. If A, B, and C are all whole numbers, then we have a Pythagorean triple. So the answer is yes, we have a Pythagorean triple. So the answer is yes, we do. And what I find important for Pythagorean triples is to write them down, because you might start memorizing a few of them. So the old 20, 21, 29 Pythagorean triple. That's the old stuff. The old 20, 21, 29 Pythagorean triple. All right, so that's it. It is a Pythagorean triple. And the more you write them down, the more you will recognize them, the more you say them out. I actually didn't know 20, 21, 29. So maybe one day I will. But if I haven't known it by now, well, when am I going to? Anyway, next question. Similar concept. The legs of a right triangle have lengths 10 and 24. What's the length of the hypotenuse? Well, we have legs, boom, boom, right triangle. The lengths of our legs are 10, 24. What's the hypotenuse? Okay, so let's set it up the same way. We know from the Pythagorean theorem, 24 squared plus 10 squared is equal to C squared. How about this? Question mark squared. Whoa, right? All we know is we're looking for the hypotenuse. Doesn't matter what we call it. So let's do some math. We got to do some 24 squared, which turns out to be 576. So 576. And 10 squared, which we know is 100. That's going to be question mark squared. So that gives us 676 would equal question mark squared. And what do we do with that? You guessed it, square root. And so when we square root both sides, it turns out that question mark is going to be equal to 26. So we have found the length of the hypotenuse. It's 26 units. And do we have a Pythagorean triple on our hands? And the answer is yes. Yes, we do. We have the old 10, 24, 26. Wait, that's interesting. 10, 24, 26. Things that make you go, Aren't these all divisible by 2? Did you ever think about that? These are all divisible by 2, right? I can divide by 2, I can divide by 2, and I can divide by 2. So not only is this a Pythagorean triple, a more apt Pythagorean triple is the old, and this isn't old, 5, 12, 13. That is a Pythagorean triple. Okay, so 5, 12, 13 is also a Pythagorean triple. Remember similarity, right? Scale factors and all that stuff. So 5, 12, and 13 with scale factors of 2 become 10, 24, 26. The old Pythagorean triple. So that's a neat little bit of information. You're welcome. So that's about finding the hypotenuse. But what if I, instead of asking to find the hypotenuse, asked you to find a leg, right? Well, have you checked your shoe? Anyway, we're going to find out the length of a leg. What is the value of x, and express your answer in simplest radical form? Well, now x is not the hypotenuse anymore, right? This is now a leg. Hopefully you see the difference between hypotenuse and leg. So how would we set up the Pythagorean theorem? Well, we're going to say that this squared plus this squared is equal to 20 squared. That's the key element right there, folks. So we know that x squared plus 8 squared is 20 squared. That's the key element, okay? So we're going to get to work. So x squared plus 64, 20 squared is 400. And so all we have to do now is solve for x squared. Okay, so we do a little bit of algebra, and hopefully we'll figure out what x is. Hopefully you know what to do from here. So what we do is subtract 64 from both sides, and it turns out that x squared is equal to 336, right? And now what are we going to do to solve for x? We are going to take the square root of both sides, right? So we take the square root. Now, what happens when we take the square root of 336? We get a crazy number, right? It's like 18 point what have you, what have you, what have you. It's a crazy number, not a perfect square. So we have to simplify this radical expression. We have to simplify the square root of 336. So something has to happen. Now, Hopefully you see that 336 is an even number. Okay, so what can we do? We can divide it by 2. Okay, so what happens when we divide 336 by 2? We have 2 times 168. Now, what's interesting about 168 is that it too is divisible by 2. So we can divide 168 by 2. So we have the 2 from what we had started with. 168 is 2 times 84. And hopefully you notice something about 84. 84 is divisible by 2. What is happening here? Oh my goodness. So we have 2 times, not 84 anymore. 84 is 2 times 42. Man, here we go again. Another divisible by 2. Holy cow. So let's continue doing this. So the square root of 2 times 2 times 2 times 42 is 2 times 21. Oh, thank goodness. Right? So what's happening here? Now this is an interesting thing that we can learn about square roots. I'm going to show you this one time, and then I'm going to go super duper 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 fast. So what we had at the bottom of this little work was 2 times 2 times 2 times 2 times 21. Now, what am I pointing at? The square root of 2, the square root of 2, the square root of 2, and the square root of 2, the square root of 21. So what does that mean? That means if I have the square root of 2 times the square root of 2, that is actually the number 2. The square root of 2 times the square root of 2, that's also the number 2. And then the square root of 21 is the number square root of 21. So we have 2 times 2 times 21, which leaves us 4 times the radical 21. And that is simplified radical form. Okay, now I have an awesome video about this as well to help you along the way, but this is pretty good too. So that's how we could find the missing leg. All right, let's do another one. Yeah, let's do more. So here's a wordy word problem. The hypotenuse of a right triangle has length 12. One leg has length 6. What is the length of the other leg? Simplified radical form. So I don't know what's going on. Let's draw a picture. Yay, picture. So we have a picture, and the first thing it says is, well, the hypotenuse is length 12. Let's do that. One leg has length 6. There, we've done that. What's the length of the other leg? I'll call it Fred. Okay, so Fred is the other leg. So how does this work? Well, we know the Pythagorean theorem. The sum of the squares of the legs is equal to the square of the hypotenuse. So let's set up the squares of the legs. So we know that we will have Fred squared plus 6 squared would equal 12 squared. So what we can do is solve for Fred. Now how are we going to do that? Well, Fred squared plus 36 is equal to 144. Okay, so Fred squared plus 36 is equal to 144. So how do we solve for Fred? We subtract 36 from both sides. And then when we have that, well, we know Fred squared would equal 144 minus 36 is our good friend 108. Okay? So if Fred squared is 108, how are we going to find out what Fred is? We're going to take the square root of both sides. Boom, boom. So it turns out Fred is equal to the square root of 108. But the square root of 108 can be simplified. Now, I don't know if you know this or not, but we've been working about a lot with 108 in class, so now I know some neat things about 108. What in the world is 108? Did you know 108 is 3 times 16? No, that's not true. That's 48. What is 3? Oh, 108 is divisible by 3. That much I can tell you. So it's 36. Come on, Chance. What's wrong with you, Mr. Katz? What's wrong with you, kid? So it's 3 times 36. That's a neat thing about 108. Okay? So if 108 is 3 times 36, check this out. What am I pointing at here? I am pointing at the square root of 3. What am I pointing at here? I'm pointing at the square root of 36. And the square root of 36 is 6. 6 radical 3. Done. Cool, great, grand, awesome. What if we were not working with that though? Okay, so hopefully that's a helpful thing for you. let's do more. Let's talk about finding a distance with a picture of a dog. Oh, I love dogs. I like math now. Okay, so this is a dog, blah, 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 words. Obstacle course, seesaw, obstacle. Now the question is, to the nearest inch, not simplified radical form. To the nearest inch, how far above ground are the dog's paws? Okay, so basically the question is, what is this leg? This is what the question is asking. What is this distance? That's the question. Okay, so how are we going to figure that out? Let's do some Pythagorean theorem. I'm going to work this a little bit quicker. All right, hypotenuse is 36, so 36 squared would be equal to 26 squared plus x squared. Now, you might be thinking, whoa, Mr. Katz, you wrote that backwards. No, I didn't. Reflexive property of equality, so take a chill pill. It's all good. It's all good. So, now I have to figure is 36 squared. 36 squared is 1296. That's a big number. And what is 26 squared? 26 squared is another big number. 26 squared is 676, and that's plus x squared. So to solve for x squared, we're going to subtract 676 from both sides. Okay? Boop. So what does that leave us with? All right. So what is equal to x squared? 6 and 6 is 0, 9, 2, 7, 12, 620. All right, so we have now the square root of 620 if we're going to take the square root. Now we take the square root of both sides. So what is the square root of 620? It's an ugly decimal. I hope you see that, right? The square root of 620 is something ridiculous. It's like 24.8999999. So do we have to leave this in simplified radical form? And the answer is no, because remember, the question was asking to the nearest inch. Well, if we have 24.899999997 in there, right? 24.899 to the nearest inch is 25. So to the nearest inch is 25 inches. So x is 25 inches. So the dog's paws will be 25 inches off of the ground. Okay, so that's how that works. Let me do one more example really quick, and then we'll call it a day. I've talked too much. So, did you know that the size of a computer monitor is the length of its diagonal? Yes. Isn't that cool? So, if you want to buy a 19-inch monitor, which is kind of small, by the way, if you want to buy a 19-inch monitor that has a height of 11 inches, well, what's the width of the monitor? Why is that important? Because my IKEA desk can only fit a certain thing. Oh, I'm using math. Right. So, how is this set up? The diagonal is 19 inches. The height is 11. What is the width? Right? So, it's 19 squared would be equal to 11 squared plus question mark squared. Okay? So, I have to figure out, well, what is 19 squared? Some number that's not quite 400. So that's 361. And that's equal to 11 squared plus question mark squared. So to solve for question mark, subtract 121 on both sides. Bloop, bloop, bloop. And now we have a 0 and a 4 and a 2. And that's equal to question mark squared. So all we have to do is take the square root of 240. Now, what is the square root of 240? It's some crazy number, right? 15.4919333. But the question is, we're not going to do this in simplified radical form. The question is, round to the nearest tenth of an inch. So to the nearest tenth of an inch, the question mark would be equal to 15.5 inches. Okay, so know your decimal places. That's going to be helpful. All right, so that's the Pythagorean theorem at work. In the next video, we'll talk about classifying triangles. See ya!